They were interrupted.
All right, so let's please continue with, did I get the name wrong? Or- okay. Huh?
Is it a robot?
Oh,
I
is it?
saw someone outside.
No, it's
You're
fine.
gonna take
Yeah.
it from him, huh?
So we're going to finish interference and start diffraction. Last time we did the soap bubble. Yes?
Is the interference on your C6 exam?
No.
Thank you.
Yeah. Yeah, you just check, it's the first 3 chapters. So, let's just do the example for the soap bubble, and then 2 more examples of interference, and then we'll finish that, and then start our diffraction. So, so we said the soap bubble looks like something like this, right? Some thickness T. The thickness of the soap bubble is T. And so you have a ray that is incident. Part of it will transmit, part of it will reflect. This is the part that reflects. There is a part that transmits and then reflects back. And then these two, they will interfere with each other. And then we might see constructive, we might see destructive interference. Let me call this one here 1, and this one 2. Over here it's air, over here it's soap or water, and over here it's again air. So for the first one here, the first one when it's incident and then it reflects, the index of refraction here is 1, the index of refraction here is more than 1. So what happens to it when it reflects? There is a phase change. It changes phase by half a wavelength. For this one, this other one, the one that goes all the way here, what happens to it is it travels a distance t this way and a distance t this way. Ignore the angle, it's approximately t. Okay. So it's t this way and t this way, so that's 2t. But because the wavelength inside shrinks by a factor of n, right? By the index of refraction. The index of refraction here is n. The wavelength shrinks by a factor of n, then the effective length becomes what? Is it just 2t or more? More, because you fit, lambda is no longer lambda, it's lambda divided by n, so you fit more of them. And so it's as if it traveled by a factor of 2n times lambda times t. So the path difference, delta r, between this one and this one will be, for number 2, 2n times t, and then for number 1, it's half a lambda, so lambda over 2. Okay? That's the path difference. So for constructive interference, we need the path difference to be what? A multiple of lambda. And for destructive, we need the path difference to be a multiple of lambda plus a half, right? Yeah. So for constructive, let's write it here. We need this, delta R, which is equal to 2nt minus half a lambda to equal to m times lambda. Okay? And this tells me then 2nt is equal to m plus a half times lambda, right? We'll move this to the other side and then factor lambda. And which tells us that t will equal to m plus a half divided by 2n times lambda. Now what's the smallest m? We have to decide what m is, right? M is an integer, but sometimes those integers don't make sense. For example, I can't put minus 5 for m. Why not? We'll get the negative thickness. The thickness should be at least 0, right? So in this case, then, what should we say? M is what?
0, 2.
Yeah, it could be 0 because you get a half. Yeah, 0 and 1 and 2 and so on. Yeah. So that's for constructive. For destructive, we need delta R, which is equal to 2 and T minus half lambda to equal to m plus a half times lambda, right? And so we can move the half lambda over there, and we can have, let me call this one here m prime, okay, for a second. M prime is an integer, okay? I'm just naming it this way. And that way, when I have this 2 and t is equal to m prime times lambda plus 1/2 of lambda. When you move this 1/2 lambda over here, half lambda plus half lambda becomes 1 lambda, so that's that. And so that means 2 and t is equal to m prime plus 1 times lambda, right? M prime plus 1 times lambda. Now, m prime is an integer, and integer plus 1 is another integer. So let's redefine this m plus 1 as m. So finally we end up with 2 and t is equal to m times lambda. And that means that t is equal to m times lambda divided by 2n. And what can we say about m? The thickness can be really thin, so it could approach 0. So I will allow for m equal to 0, 1, 2, and so on. So that's that. The example I wanted to do is the following. Suppose we send blue light and red light. So we send 2 beams of light on the soap bubble. So suppose so this is an example. Suppose we send lambda equals to 662 nanometers, and lambda is equal to 465 nanometers on a soap bubble. So suppose we set this on a soap bubble. We don't know the thickness of the soap bubble, and here's the question. What's the smallest thickness of the soap bubble so it will appear red? By the way, I gave you the 2 wavelengths. One of them is blue, the other one is red. Which one is blue and which is red?
662 is red.
Good. And the blue is the shorter wavelength, right? Okay. So 465 is blue. So suppose we would like, if the soap bubble appears red, what is the smallest non-zero thickness of the bubble? What's the smallest possible non-zero thickness? So what do I want? So what happens here? We send blue and red, and then at the end it will just appear red. So what do we want? Blue to go away. Yeah. So blue needs to cancel, which means blue needs to construct or destruct. Destruct. So blue needs to interact destructively or interfere destructively. So when you get rid of the blue, what remains will be the red. Okay. And So that's the solution. So we want destructive interference for the flu. So destructive means I need this. So T equals to M lambda over 2N. M is 1, right? Smallest non-zero. That one's 0. So smallest, the next smallest number after 0 would be 1, right? So 1. 465 nanometers divided by 2N. What do you think N is for a soap bubble, approximately? How do you make soap bubbles? You add soap to water. So it's going to be probably water. So let's assume the index of refraction to be about 4/3. Okay, 4/3, or 1.33. So do that. And give me a moment to actually calculate it. What do you got?
175 nanometer.
175?
Yes.
It's going to be about 175. Or maybe exactly 175, I'm not sure. So 175. Yeah, I guess it's divisible by 3, yeah. So, yeah, works out. Okay. Let's go to the next. I have two examples on interference. Gina, did you have a question?
No, I'm just.
Oh, okay. So here is the next question. Next question is going to be about interference, the double slit interference. So here is a double slit. Okay. The distance between the two slits is going to be D, right? No problem there, right? And we have a screen here. And the screen is very far away, so we can use small angle approximations. And we're going to so if we send light here, we just get the usual thing, right? D sine theta equal to M lambda for constructive. But somebody comes along and says, you know what? Let's place some transparent material here in front of it with some index of refraction. So we're going to place some material here, and that material will have an index of refraction L, and the length of this material is L, or the width, the length. And the question is, what's the condition for constructive interference? So, for example, you get the light that comes in, and it gets here. So it has to travel. And the question, what's the condition for constructive interference? Okay. Light here, or any ideas on what to do? Ignore the angle, like the fact that the light goes a little bit at a certain angle here. That distance is still L. The horizontal distance is still L. So any ideas what to do? Constructive, we need what? The path difference to be a multiple of lambda, right? So we need to find delta R and then set that equal to M lambda. That's what we need to do. So this one travels a distance L in air here. Before we didn't care about it because this one travels a distance L in air, this one also travels a distance L in air. But now we have this, so I need to go back all the way here. So this one travels a distance L in air. This one travels a distance L in this material. So what's the path difference? The path difference is going to be this. First of all, here, this one traveled L, this one traveled L, but it's in a material of index of refraction N. So what's the effective length here? Is it just L or more? More. L times N. Ln, or NL. Okay. So you got N times L. This one traveled L only, so the difference between them is this. NL minus L. And now this part, when they travel from here to here, you got this one traveled an extra what? What's this distance? At this angle, let's assume it's theta. D sine theta. So plus another D sine theta. That's the path difference between them. Okay, that's the difference in path. So you got this much due to the, before even the slits come in, that's the shift, and then plus this additional distance due to the angle. Okay. And so if I'm looking for constructive interference, what should I set this thing equal to? What should this equal to? You know. M lambda. Yeah. Yeah. M times lambda. Yeah. M times lambda. So we got here, you got what? N minus 1 times L plus D times the sine of theta is equal to M times lambda. And so D times the sine of theta is equal to M times lambda minus N minus 1 times N, right? And that's it. D, yeah. So that's for this one.
You're trying to find the distance?
I'm trying to find at what angles I have constructive interference.
Got it.
Yeah. So if I divide both sides by D, it will give me the angle, right? If I divide, let's divide both sides by D. So this tells me at what angles I will find constructive interference. Anyone knows how to do destructive interference then?
Equal to M plus 1/2.
Yeah, that's it. There you go. Yeah. One more interference. So now let's consider a double slit with the following. So let's consider, so this is another example. So these are the two slits. Okay, these are the two slits. And this slit here, this one, let's see what drew. The thickness of these walls is T. The thickness of the walls is T. And the distance, as always, between the two slits is D. But what we're going to do, it's kind of similar to this one, but instead of having a block right before the slit, we're going to insert some thin film here index of refraction n. Maybe, so this is n. So maybe it's water. So a thin film filled with water. So n is equal to 4/3, okay? N is equal to 4/3. Right? So you got two slits, and this way it's index of refraction n, and n is 4/3, and the thickness here is t. Right? And we would like to know what should the thickness be in order for us to have what should T be so that for constructive interference we have d sine theta equals to m times lambda. What should this width or thickness be in order for this to be the case? And m is an integer. M is an integer. What do you think we should do? Difference in path. Yeah, you need to find difference in path. First of all, before, this one travels a distance t, but this one travels a distance, it's also a distance t, but it's effectively n times t, little n times t. Okay, so that's that. So let's write it. So we have, to start with, here's delta r. We usually do the bottom minus the top. So the bottom travels the distance t, the top travels n times t. And then how about from this point and on? What's the path difference? D sine theta, good. Yeah, this is theta, right? So this part is d sine theta. So plus d sine theta. And we want that to equal to what? For constructive interference? Yeah, times lambda. Yeah, that's what we need that to equal to m times lambda for constructive. Well, let's see. Let's move this to the other. I would like it to equal to m lambda, right? And then we solve for d sine theta. Let me. Yeah, I think that's fine. I was going to rename this to another integer name so that at the end we end up with the same name here, m. Can I name this one here as some integer called capital N? How about that? Capital N. N is an integer. Again, it's 1, 2, 3, 4, minus 1, minus 2, 0. Okay, so I get the following. Let's move to the other side. So we get d sine theta. When you move this to the other side, you get n lambda plus nt minus t, right? N times t minus t. And so you get d times the sine of theta equal to n times lambda plus n minus 1 times t. Okay? N minus 1 times t. So I want this. N is an integer, capital N is an integer, and I still want this right-hand side to be what? Yeah, it will be m lambda. Yeah, I would like it to be m times lambda. This will allow me to solve. So I get this. Let's move n lambda to the other side. So I get this. N minus 1 times t is equal to m minus capital M times lambda. n minus 1, n is 4/3, right? N is 4/3 times t. Uh, 4/3 minus 1 is 1/3, so I get 1/3 of t is equal to n times capital N times lambda. So t needs to equal to 3 m minus n times lambda, right? What would be the requirement? M is an integer and n is an integer, so their difference is also an integer. Okay? Yes, we agree? M is an integer and n is an integer, so the difference between them is also an integer. But we need one little requirement, which is m needs to be greater than n, right? M needs to be greater than n, or at least equal to it. Otherwise, you get a minus negative number for t, which is that's it for this one. And yeah, I think that's enough for this. I had another one in mind, but maybe next time. Okay. So we'll now start the next topic, which is diffraction, right?